Alright, so here I want to talk about a reaction called the E2 reaction. Now E2, well, E stands for elimination. You've seen elimination reactions before. They're ones that form alkenes. 2 means the same thing as 2 means in the SN2 reaction, meaning bimolecular. So there is something of a difference between E2 and SN2 reactions, but they also have some similarities. So what I want to go through is just the basics of the E2 reaction. We'll do some comparisons with SN2. I'm going to have a separate video showing how you can predict products that are either going to be E2 or SN2. So here's an example of an an E2 reaction. We have a tertiary alkyl halide, and this guy is hydroxide. Now you guys have seen that before. It's a strong nucleophile. Now the fact of the matter is the vast majority of compounds that are strong nucleophiles are also strong bases. Alright, so OH minus, perhaps methoxide, OCH3 minus, maybe NH2 minus. These would all be good examples of strong nucleophiles, and because they're small, they're strong nucleophiles, but they're also strong bases. So the big difference between a nucleophile and a base is what they attack. Nucleophile, you've seen before, attacks a carbon, and a base, hopefully you'll remember from your chemistry 1212 class, a base attacks hydrogens. That allows for an elimination to occur. In fact, these reactions are routinely called beta eliminations, and you might have a question of well, why is it called beta? What does the beta mean? Well, let me just show you the mechanism. Okay, so the E2 reaction, just like the SN2, occurs in one step. The 2, of course, as we said before, means it's bimolecular. So when we look at the rate law, the rate is equal to K times the concentration of both the substrate and the concentration of OH minus, which in this case we'll just call the base. And I don't care whether you say base or you say OH minus, it doesn't really matter. So, bimolecular, so both species are involved in the one step. Alright? So let's look at the mechanism, okay? And we can illustrate the mechanism with this reaction. Now, the concept of the term beta, alright, these Greek letters mean something specific with respect to carbons in your substrate. So the carbon that's usually termed alpha is the carbon that bears the leaving group. Okay. Now, if you know much about Greek, alpha is the Greek letter for A, beta is the Greek letter for B. So beta, if alpha is the first carbon, then beta is the second carbon. So the beta carbon is always the carbon that's next to the alpha carbon. So these 3 carbons are all exactly the same. They can all be classified as the beta carbon. And so the reason these sorts of eliminations are called beta eliminations is because of the fact that to get to a product like this, you have to lose the leaving group and you have to lose a hydrogen. You can't lose them from the same carbon, otherwise you'd have a carbon with only 3 bonds to it, or 2 bonds. So what happens is the base, the OH minus here, is acting as base, and it removes the hydrogen from the beta carbon. That's why it's called a beta elimination. So when that oxygen forms a bond with that hydrogen, this bond then has to break, and that bond sends its electrons down to the carbon, the bond between the alpha and beta carbons, forming a double bond, and in the process kicks out the leaving group. And as you can see, a result from that is you have Br minus. The OH minus has grabbed H to get H2O. But the most important product is this one. It's the organic elimination product. Alright? Okay, my thing has disappeared. Okay, there we go. Alright, forget about that. That's not a 6. That's just because my bollocks. My little arrow disappeared. Anyway, let me just delete that. The joys of creating videos. Sometimes things get all foo-bad. So let me see if I can just fix that. Just talk amongst yourselves for a minute. All right, okay, so the most important product is the alkene product. And can you guys see there were 1, 2, 3, 4 carbons in the starter material, and then there's 4 here. Okay. So we said typically that strong bases are strong nucleophiles. There are, however, some species that are only bases. In other words, that are strong bases but weak nucleophiles. And as you would imagine, if a nucleophile needs to get into a carbon, the smaller it is, the better nucleophile it is. Or conversely, the bigger it is, the worse nucleophile it is. So there are a couple of bases that are used for very specific things. All right. One of them is called the tertiary butoxide, or T-butoxide. That's this guy right here. It's an O-, just like the methoxide and the hydroxide, but with these 3 methyl groups. This is essentially a T-butyl group. And it's big and bulky, meaning this does a really poor job of acting as a nucleophile, but does a great job of acting as a base, because the hydrogens are always on the outside of the molecule. For the same reason, this molecule here called DBN, it's these 2 fused rings with nitrogens there. The nitrogen are the basic parts of the molecule. But again, because this is really big, this DBN and this T-butoxide, they're called non-nucleophilic bases. In other words, they only act as bases because they're too big to act as nucleophiles. So if you want something to virtually guarantee an elimination reaction, then you use a big, strong base like this. These guys are also strong bases, but they can act as nucleophiles as well. So when you have a situation where something could act as a nucleophile and a base, well, it actually could do both. Ultimately, what determines whether it does or not is the identity of the alkyl halide, and we'll talk about that right now. So let's talk about the structure of the alkyl halide, or the substrate. All right. Now we know, or you guys know hopefully, that if you look at the idea of primary, secondary, and tertiary halides, and I was to ask you, which sort of halide, primary, secondary, or tertiary, is favored in an SN2 reaction, you would tell me, hopefully, that primary alkyl halides are favored in SN2 reactions, because the nucleophiles have easiest access to the primary carbon. So what if I told you then that the order of favored carbons, or favored substrate, is actually exactly the opposite in an E2 reaction? All right. For one thing, this guy doesn't have to get all the way into the carbon, it just has to attack a hydrogen. But then the question is, so why is E2 favored? Because you would think that, well, if E2 and SN2 are kind of the same, wouldn't they both favor primary? And so the rationale is this. All right. Let's say we have a compound like this one here, and then maybe this one here. Okay, 2 alkyl halides. If we have something that's a strong base, all right, let's for example use our tertiary butoxide. I'm just going to say OTBU, just 2. It's a shorthand for tertiary butoxide. If I throw in my strong base here, and I remove a beta hydrogen, or hydrogen on the beta carbon, so I have a beta carbon here, and I'm going to remove the hydrogen from this beta carbon here, then the product I end up with, in this case, my double bond is between my alpha and beta carbons, and it's this, because that's my alpha carbon and that's my beta carbon. If I do the same thing here, my elimination product is going to be this. And so the rationale for why this sort of substrate is preferred in an E2 reaction is the stability of the alkene that we get out. Alkene stability is based on how substituted it is. All right, for example, this is called a mono-substituted alkene because there's one carbon group coming off it. This would be a di-substituted alkene. It's a bit more stable. This guy would be a tri-substituted alkene. And the most stable alkene you can have is a tetra-substituted alkene. Now, you don't see tetra-substituted alkenes as a result of elimination reactions, but if you can form the more stable alkene, you will. So that's why primary alkyl halides don't like to form don't like to react in E2 reactions, simply because the alkene they get out is not all that stable, because this is a mono-substituted alkene versus a tri-substituted alkene here. So what you'll find is, if you have a tertiary substrate with a strong base, that's pretty much a guarantee you're going to have an E2 reaction. If you have a primary substrate with something that's a strong base, it's also a strong nucleophile, you're going to have SN2. Now, like I said, I'm going to have a separate video outlining how to predict between E2 and SN2, but I just want you guys to understand in this video what the E2 reaction looks like. So you always end up with the double bond formed between the alpha and beta carbons. All right. If we look really quick at this molecule, though, can you see if this is the alpha carbon, there's a beta carbon here, but can you also see there's a beta carbon here and a beta carbon here? Both of these would be the same, so I'm going to call them both beta 1. This would be beta 2. There is a reason why the hydrogen from beta 2 is removed rather than the hydrogen from beta 1. And let me see if you guys can figure that out. Let me draw out the product that you would get if we remove the hydrogen from the beta, from one of the beta 1 carbons. What we get would be this. There's the alpha carbon, there's the beta carbon. I don't know if you guys can predict it or not, but this alkene is tri-substituted. This alkene is only di-substituted. The rule here is that the most stable alkene product will predominate in an elimination reaction. This is something called the Zaitsev rule. It may not be the only product, but the Zaitsev product is going to be the major product in an elimination reaction when we have two different types of beta hydrogens. All right. Okay, that is the E2 reaction. Watch my next video to show how we can tell between when the mechanism is going to be E2 or SN2. Ultimately, it comes down to the base and the structure of the alkyl halide.